We can't hear you, sir.
Now you can hear me?
Yes, sir.
Okay, so I hope you can hear me now. We can hear you. Okay, great, great. Okay, so today we are going to solve worksheet number 4 together. Worksheet number 4. And this is 3. We are going to solve worksheet number 4, right? And this worksheet is just about the complex numbers. So I will just switch to the projector. I hope you can see it. If you can't see it, it's online on Island.
We can't see it, sir.
Now you should be able to see it, right? Okay, before I start with worksheet, I just want to remind you about some of the theory that we did, and you will need it definitely for solving the worksheet. So as you see, it's about complex numbers. So the topic here is complex numbers, and what we learned during the class. If you remember, we defined complex numbers. So just let me give you a summary of the things you need here, the major, let's say, theory behind that, and then we will see how to solve. All right, so the first thing here is, just 1 second, I need to close the door here. So first of all, we define the complex numbers, and then we define some basic operations on complex numbers. So this is what I'm going to just recall very briefly here. Okay, so we defined the complex number. Let me take the blue. I hope you can see it here clearly. So zoom a little bit out. Complex numbers. So we said that the complex number is a number that contains two components, where one is called the real part. So usually we will be using Z to define the complex number. We write it as an ordered pair or as real part, and this y is called imaginary part of z, and this I is just the square root of -1, which is not possible in the real numbers, so that's why we just expand the real numbers to be able to include negative roots. Okay, so this is the definition. We defined operation of complex numbers. So given two complex numbers, let's say z1 equals x1 plus I y1 or y. So I and y here we can change them, no problem. And here x2 plus I y2. So given two complex numbers, we add them up by adding components. So in this case, we add x component to x component and y component to y component. So this is how we add complex numbers, and the same also for subtract. So here, let me just define z1 plus z2. So I add x1 plus x2, and this will form the real part of the sum, and here either y1 plus y2 with I in front or after, and here z1 minus z2, and here you need to just make sure that you have the correct sequence here, because as you know, the subtraction is not commutative. So that means here z1 minus z2 is different than z2 minus z1. Now multiplication, whenever you think about multiplying, okay, multiplying two numbers. So at the beginning we use the asterisk, but then we just leave it. So we can say also z1, z2 with a dot or without a dot. And now here, let me just write the two numbers here. So x1 plus x2, plus y1 I, and here x2 plus y2i. Okay. And wherever we talk about multiplication, we talk about polynomial. So it's just similar to multiplying an polynomial with two terms, two polynomials with two terms. So here this x1 will be multiplied with this first element with the second element, and the same here for the second element. And okay, so multiplication is, if you like a polynomial. Actually later we will introduce the so-called polynomial theorem for evaluating exponents of such multiplications, and also there we can use this polynomial theorem to evaluate exponents of complex numbers like x, z here to the power 7, 6, whatever. Okay, now if I multiply this out, I hope it's clear for everyone from the class that I had here x1 y2i plus x1 x2 y. So here I have x2, I just rearrange it, y1i, and then here this is the special term, if you like. Here if I multiply y1i with y2i, I got y1 y2i squared. Okay, and we said that this I squared here in complex, let's say, calculations here is just -1. So this term here becomes negative y1 y2, and this is a real number. This is important. So now it's even though I'm multiplying two complex, let's say, exponents here, I got a real number, and this goes to this part here. So this one, if you like, it goes to this part, and if we group these, the multiplication becomes x1 x2 minus y1, y2. And this is the real part of the multiplication. And here, if I take I as a common factor, I have x1, y2 plus x2, y1, I. So if you like, this is the real part, this is the imaginary part of the multiplication. Any questions so far? I don't see anything here on the chat. Questions? Okay. Now, when it comes to division, it's a little bit. I didn't tell you here that this form here, maybe this is. I hope you still can see it. This form here of writing a complex number where we can isolate the real number part and the imaginary part. We call it either standard, or sometimes it's also called Cartesian form. Okay, and this means that we can write x and real part and y as a complex or imaginary part. Now, using the numbers in this form and dividing them, let's assume we start with z1 as z2 as defined above. Here, z1 divided by z2 is equal to x1 plus I y1 over x2 plus I y2. Okay. Now the thing is here, we define something for a number, any complex number. We define the so here let's start with any number. Let's say z equals x plus iy in general. Okay, so this is a definition of what we call conjugate. Conjugate of a complex number, we just use the bar here on top of the number. And this is nothing else than just negating the sign of the imaginary part. So here, if I have positive, it becomes negative and vice versa. This is what we call the conjugate of a complex number. And this conjugate has the feature that if I multiply a complex number with its conjugate, the middle term will cancel out. So I will have, if you like, ultimately I will be getting, if you apply this rule, what do we get? We get x squared minus y squared. And the imaginary part will cancel out because I'm going to get x times yi in once in positive, once in negative, and it will cancel out. And this is a very nice feature, because if I multiply a complex number with its conjugate, I will be getting a real number. Okay, I hope this is clear for everyone. What is the conjugate of a number and why it is it has a nice feature. And this trick actually I'm going to use with the division. So if we go back here to dividing these two numbers, now look at this number here in the denominator. If I multiply this with x2 minus iy2, then I will be getting a real number. So in this case, I will get rid of the imaginary part in the denominator, which causes a problem in real or complex calculations. So I will multiply here with the conjugate of the denominator, x2 minus iy2. Okay. Now to keep the ratio of this original term, I will also multiply the numerator by the same, because ultimately it's just like multiplying by 1, which does not change anything in the equation. Okay. So if I just continue here, I will be having a very nice way to evaluate this quotient. Okay, so here I will be having x1 plus y1 times x2 minus y2, and then here in the denominator I just have x2 squared minus y2 squared, because I'm just multiplying with the conjugate, and this is very nicely or elegant way to get rid of the I in the denominator. And here, of course, you can multiply this out and so on. Okay, so this is, I think, all the theory. Let me just check. Yeah, there's something else here that we need, and this is the quadratic equation of roots of quadratic equation ax squared plus bx plus c. And I think you know this from school, that you have two roots, x1 and x2, and these are equal to minus b plus minus square root of b squared minus 4ac. This you need maybe in the last question over 2a. Now, if you consider these two roots here, so this is once plus and once minus, so that's why you get two values here. And you all know that this part here, if it's less than 0, then we have the roots are in C, are complex numbers, okay? And of course, if you have a negative value here, then you have an I, which is square root of -1. And then you will be getting ones and positive ones and minus. That means these two roots are, if you like, conjugate to each other, because one positive, one negative. Okay, so wherever you have this amount under the root in negative, then you end up of having complex roots. Okay, so any questions so far? Any questions?
Yes. Since building products and processes, we missed the last 1.5 hours from last week, or it was even 2 weeks ago, I guess. Should we just like look into the script, or what did you do? Do you recommend to keep track?
Is at least here. Media board. Can you say something now?
Hello? Hello? Do you hear me?
I'm sorry, I didn't. Your mic is unmuted.
Yeah,
You
that
tried
works.
to say something. Okay, let me just try this. Media board, Lautsprecher. Now?
Yeah? Do you hear me?
Now I can hear you.
Okay, perfect. I think it was already 2 weeks ago. There was a lesson which the BPP students couldn't attend due to chemistry at the same time.
Yes, yes.
And should we just like look at the script to keep track, or what do you recommend?
No. I will. First of all, if you don't have problems today with this worksheet, I uploaded actually the answers.
Yeah.
So these basic operations, do you have any problems with these?
No. No.
No problems. Okay, so then just please look the answers, look them up on the iLearn, and tell me if you need any problem. I will summarize this lesson actually for the group that didn't continue with us last week or 2 weeks ago, and we will do it together now. Okay.
Okay. Thank you very much.
Okay, you're welcome. So it's about. Hold on. It was about roots and what else? Powers. Yeah, roots and powers of complex numbers. Okay. Okay. So now for this worksheet, you just go to the worksheet. It's straightforward. Actually, all these operations are straightforward. Let me just zoom this. Don't know what's wrong with this device here. Can you see it clearly or just I?
No, it's blurry. There's probably a filter.
Yeah,
Or,
okay,
know.
so let me just focus. No. This is technology. You get rid of something, you have another. Anyway, let me write something, then it will be power and no, it's not here. So let me just focus this again. I have no clue what is this. Ah, okay. So let's see the zoom. So what's the problem here? You still can't see it clearly, I assume, right? I have no idea.
Oh, sir.
It's blurry.
No.
Yeah, still blurry.
Yeah. Now, oh. Now it's clear, I hope. Power and roots. Of complex numbers. Yes, come on. Okay, so power and root of complex numbers, we said that a complex number can be given in so-called standard form. And you can think about a complex number here as a number on the XY plane, where we assume that the real part is along the x-axis and the y part along the y-axis. And we can think about it as an ordered pair where the imaginary part is always the y. So any complex number here is just, if you like, you can think about it as an ordered pair with x, y coordinates. And then as we define theta, if you remember, for the polar coordinates, so we have here the x component and, sorry, this is the y component, of course, and this is the x component. And if we consider this line connecting the point with the origin as r, then we have corresponding to this what we call the polar coordinates of a complex number. And this is very important, how to get these polar coordinates. So given a number in xy coordinates, or what we call standard coordinates, we evaluate the polar coordinates as there we need r and we need theta. So this number is uniquely identified using these two parameters. R is sometimes also referred to as the magnitude of Z, is the length of this line connecting the origin to the number. And as we evaluated it for, you remember, a two-dimensional vectors is just the square root of adding up the X component and the Y component. You can think about it as using the Pythagorean theorem. So you know that R squared equals Y squared plus X squared, because this is a right triangle. Okay, so whenever we are given XY coordinates, we evaluate the corresponding R or Z, and the angle is, look at this here. Tangent theta is equal to Y over X. I think you know this from trigonometry at school, that you have a right triangle. It's the opposite side divided by the adjacent side here. So here, if I just take the inverse of this tangent, I end up of evaluating this theta. And always remember that evaluating this angle depends on the simple fact where this angle belongs to which quadrant. You remember we defined the quadrants, if you remember, when we introduced this, as the 4 quadrants, starting with the first here counterclockwise. And we said that in this quadrant, first quadrant, the angle, if we assume we start at this here, positive x-axis counterclockwise, it starts with 0 to 90 degrees in this quadrant, from 90 degrees to 180, in third quadrant from 180 to 270, and from 270 to 360 or 0 is the fourth quadrant. So here you have to be careful, especially in these two quadrants, because if you have X and Y different signs, then you end up with having the same amount here. So here, if you get a negative, you need to know that this negative, it means it's the shortcut from the x-axis to the line connecting the origin to your point. I hope this is clear. So from the very, very beginning, just ask yourself, whenever you have a complex number, to which quadrant this belongs before trying to evaluate the angle, because if you get it in the negative, it will be just there will be ambiguity there, which of the quadrants 2 or 4 this belongs to. Okay, so for a given complex number in standard or Cartesian form, we evaluate the polar coordinates using this set of equations here. Is this clear how to evaluate this? This fly is very keen of learning mathematics, so okay. Clear? No questions so far here regarding this point, because this is actually a very an essential step here, that you need to know how to calculate the corresponding complex, standard, and polar coordinates for a complex number and get one from another. If you have a polar, how to get the standard, and if you have the standard, how to get the polar coordinates. Okay, if you are able to do that, then you will see that the many calculations using complex numbers are very, very simple. So the first thing, how to evaluate the power of complex number. There is a very famous theorem that was introduced by French mathematician D. Moivre, and the theorem is called after him, theorem or rule or whatever. So here we are given a complex number. Very important here, Here, by the way, if you have the polar coordinates, you want to write z, then you just write it as r times cosine theta plus I sine theta, because here you know it from physics maybe also, that this x component is just r sine theta. This one here is, sorry, this is r cosine theta, this is r sine theta, and then the expansion here depends on r, so that's why we multiply with r. So this is, if you like, the polar coordinate or polar form of a complex number. Okay, so given such a number in polar coordinate, given a complex number z in polar coordinate, that means that this z and a number n in a natural number, let's say starting with 1, 2, and so on, then okay, the number must be here. Maybe I will just underline this, given in polar coordinates. So if it's given in other coordinates, you just need to transfer it to polar coordinates. Then z to the power n is given by r to the power n. So the number will look like this in polar coordinates. Then cosine n times theta as a real number multiplication plus I sine n times theta. See how easy is it to evaluate such exponents if you have it in polar coordinates. So all you need to do here, just n, evaluate r to the power n, and then here, very interesting here, multiply n with the angle to evaluate it. Okay. By the way, here you can use the angle either in exponential or in sorry, you can use the angle here either in radian or in degrees. Okay, shall we take an example here? Okay, maybe this stage evaluate 1 plus I to the power 6. Okay. Of course, here we can, I think one of the questions in the worksheet that you can evaluate this as repetitive multiplication, right? So this means it's 1 plus I multiplied by itself 6 times, right? So this is, you just multiply it 6 times. If you want just to multiply 2 and then this multiply the result 3 times x squared, whatever squared. But this is a tedious procedure, especially if you have to multiply it even more often than 6 times. So that's why using this theorem is very simple. Okay. Now, to be able to use De Morvier's theorem, we need to transfer this in so-called polar coordinates. So the first step here, the solution for this, let's call this number z. Okay. Now, who's going to tell me what is the magnitude of this number, which is r here? So if we write the number as polar coordinates, we are almost done. Okay. First of all, this number z, where does it belong to? Which quadrant? Anyone can write on the comments which quadrant, or just say it. I can hear you, by the way.
The first.
The first, obviously the first. And here by default, we don't have a coefficient of I. It means I is 1. So this is definitely in Q1. Why? Because X is positive, Y is positive. Okay. Now, what is the magnitude of this number? What is this distance, this z here, or r? It's 1 squared plus 1 squared under the root. Here you have to be careful. I saw in many of you solving the problems. If it's negative, they don't square the negative. So here we don't have negative, but then you need to square the negative here, and we get just square root of 2. Okay? Does that make sense for everyone? Is it clear? Okay. Now theta is equal to tangent inverse of y over x. Y is 1, x is 1. So it's tangent inverse of 1. Who's going to tell me what is this angle? Tangent inverse. I hope that everyone can evaluate this using his or her calculator. And you need to be careful here for the scaling of your calculator, whether it's using the radian or the degrees scale. So who's going to tell me what do you get here? What is theta? Now we agreed that theta is in the first quadrant. First quadrant, we said it's between 0 and 90 degrees, right? So we expect it between 0 and 90 degrees, excluding 0 and 90 degrees because they are on the axis. So no one can calculate tangent inverse of 1. Come on, guys.
45.
45 degrees, right? It's 45 degrees. Thank you. So theta is 45 degrees. We know n, we know theta, we know all the parameters we need for de Morvier's theorem. And now we can evaluate this exponent, okay? So that means here 45 degrees, or by the way, it is pi over 4. I don't know, pi over 4, 3.14, maybe it's 0. I don't know, 4 something. Okay, and radian. Okay. And as I told you, in this particular formula here for de Morvier's, you can just plug it in, whether it's degrees or radian. So let's take it for the degrees. Let me just try to squeeze it here in these two lines, the result. So z to the power 6 according to de Morvier's theorem equals to r to the power 6. R we evaluated as square root of 2 to the power 6, right? Multiplied by cosine of n here is 6. So 6 times 45 plus I sine 6 times 45. Okay, I just evaluated or plugged in the values in de Morvier's rule. So this is my n. I multiply it here with the degree, and here I just raise the power to this. Okay? Is it clear, this step? Okay. Now here again, what is square root of 2 to the power 6? Let me just try to explain it on a separate page maybe.
2 power 3.
Square root of 2 to the power 6. I hope that you are familiar with these. So what did you say? 2 to the power 3, right? Yeah, which is 8, right? Yeah, correct. So if you have any problem with that, remember always that the root here, so maybe this rule I will just remind you. If you have here n and here you have, I don't know, whatever number, x to the power m, okay? This is equal. So this nth root is just x to the power 1 over n all to the power m. I hope that you are familiar with this rule. Or you just say this is x to the power m over n. Okay. Now here, this is the second root, of course. So I have here 2 to the power 1/2 all to the power 6. And this is 2 to the power 3. Because according to the exponential rules, if you have a root, if you have an exponent to another exponent, you just multiply them. So here you will just cancel the 3 with the half, and then you end up of having 8. Anyone has problem with this simple calculation? Okay, so let me just continue. Yes, question? If you don't have question, please switch off the mic because it's a little bit noisy in the background there. Okay, now let me just continue here. So we said that, please switch off your mic. I don't know who's that. Shadi, please switch off. Do you have a question? I couldn't hear you. I just heard noise. No, this is for PP. This is only you check the schedule. This week we don't have IE and ESE. It's only for those who didn't manage to attend the rest of last week's session. So it's only for PP. Okay. Any question here? Shadi, did you try to say something? I just hear noise. I didn't get you. Okay, so let's continue. If there are no questions, let's continue with this particular example. So we said here that the square root of 2 to the power 6 plus, multiplied by cosine. Let's multiply it out. 6 times 45 is 270, right? Plus I sine 270. Okay? And this is equal to, we evaluated this as 8 times. What is cosine 270? 270. What is cosine 270?
0.
0. And sine? Is it 0 or negative 1? It's negative 1, right?
Negative 1, yeah.
Negative 1. So this is plus from the formula. And then you have I. Okay? So all in all here you get 0 minus 8i. So this is the answer. I think maybe this is one of the questions in the worksheet. I'm not sure. It's similar actually to one question that you have there. But there I wanted you to solve it as a repetitive multiplication rather than using the de Morvier's theorem. So you see here, de Morvier's theorem is very easy and straightforward. So whenever you are asked to evaluate a power of a complex number, 2 steps. First of all, if it's given in standard form, you just transfer it into the polar form, and then you apply the De Morvier's theorem to get it into the to get the answer, and then you are there. Now here, maybe very important note here. If you have you are multiplying out large numbers, especially if you are using degrees, theta or tangent of theta is equal to theta plus 2, let's say k times pi. Okay, so if you add any full circle to the angle, you are there. So this is what we called, I think we did that in the first sections, what we call a periodic function. So for instance, this theta, if I just take a full cycle here, then I end up of having the same. So this is theta plus 2 pi, theta plus, sorry, 1 pi, 2 pi. So if k is 1 times 2 pi, 4 pi, 6 pi, and so on. Okay, so for instance, if you got an angle 700, this is similar to dividing by 360 and taking the rest. Okay, so for instance, if you have the angle, let's say 700 degrees, this is equal to 360 times 1 plus what we end up 340, right? Okay, if you have an angle, let's say 1500 degrees, then you have here, I don't know how many 360s have, maybe 3 times 360, and then whatever here the rest is the angle. So this function in mathematics we call the modula or modulo function, which gives me the rest of dividing a number by another. So this is some trick that enables you to easily evaluate. Of course, you can go to your calculator and then plug in tangent or whatever cosine of this, cosine and sine of 1500, but if you don't have calculator, it's easier to evaluate it this way. Okay, now let's move to any questions regarding De Morvier's theorem, powers of complex numbers. Okay, now we are going to evaluate the roots. Now, evaluating the roots using complex numbers is a little bit different than evaluating the roots in real numbers. So roots, I hope that everyone, we just introduced now the notation. What does it mean that a number is a root of the other? What does it mean? Anyone can explain to me? So a number, let's call it U, is called, said to be a root, an nth root of another number Z, so let me just underline these numbers. F. What does it mean when I say that 2 is a third root of 8, for instance? What does that mean? Anyone can help me out with that? If I say 2 is a third root of 8. Is it a third root of 8, 2? What do you think? Is it? What I'm asking is 2 a third root of 8? No answer?
Yes.
Yes, it is. How do you verify that?
Well, reverse engineering, I say 2 times 2 times 2 is 8.
Exactly. This is exactly what's meant here. Yeah, we say that a number u is an nth root of a number z if u to the power n is equal to this number. Okay. It's just like your colleague said, is that 2 to the power 3 equals to 8. So 2 is a third root of 8. So in general, or we can write it if we just take the nth root of both sides, then you can write it that u equals z to the power 1 over n, just like what we did before for the square root. You remember we said that the square root. So example, let me just put this example maybe here in another color. So let's take an example. 2 is a third root of the number 8. Okay, so 2 to the power 3 is equal to 8, or I can say the 8 third root of 8, which is 8 to the power 1/3, is equal to 2 equivalently. Okay, so this is just a definition. Now, if we want to apply this, just using this fact to the De Morvier's theorem, let's see what we get. So let's assume we have two numbers. One we call z and the other we call u. So z is equal to, let's assume we have the two numbers in the polar coordinates. So one is cosine theta plus I sine theta, and the other u is equal, let me just take here different names here, maybe b its magnitude, and here cosine, let's take the angle here alpha plus I sine alpha, and given a number n is a natural number. So this is what we are given. Now the fact that then if z equals to u to the power n, that means if u is an nth root of z, then we have here to the left hand side r cosine of theta plus I sine theta. So this is the left hand side. Right hand side, I have what? I have p u to the power n. So p to the power n using De Morvier's theorem. And then I have here cosine of n alpha plus, I just applied the De Morvier's theorem. Applied De Morvier's theorem. Now, two numbers in polar form are equal if and only if the magnitudes are equal and the angles are equal. So from this equation, it follows that, as expected, r equals p to the power n, or equivalently here you can say that p is equal the nth root r to the power 1 over n, the nth root of r. Okay, so with magnitude we have no problem, and this is by the way, this root here is a root of a number because both r and p are real numbers. Now we come to, if you like, this is if and only if. So, and what about the angles here? The angles here also must be equal. That means here this theta, it must be equal to n alpha. Okay, theta is equal to n alpha, but because of the fact that theta plus 2 pi is again the same as theta, because of the fact that the trigonometric functions are periodic, it's not only one solution there. So theta plus any 2 pi will be solving this equation here. So that's why here it's not only theta, any 2 pi times any k. Okay, so here if we multiply with k is equal to n times alpha, and k here is equal 0, 1, and so on. Okay, this is just because of the fact that I demonstrated on the previous page that the trigonometric functions are periodic, adding any 2 pi. So if you add 0, of course you have the same theta. If you add k is equal 1, then you have 2 pi, and so on. I hope this is clear where this comes from. This is because of the fact that the trigonometric functions are periodic. Now if we solve this for for alpha, this equation here, let's solve it for alpha. Let's solve this equation for alpha. What do we get? So let me just do it here in red. So alpha is equal to, so that means here in the left hand side we need to divide everything by n. So theta plus, let me just put this 2 pi k or 2k pi over n, and you can just split it here, theta over n plus 2 pi k over. Okay, actually we are there. Okay, now that means here, that means to evaluate these roots, I need to evaluate I evaluate these roots by plugging in the k, 0, 1, and so on. Now where to stop? This is the thing here that I just left here and open, and here. Now where to stop is actually given by this very famous theorem, which is, if you like, a version of what's called the fundamental theorem of algebra. So this theorem says that every complex number has exactly n distinct nth roots. Okay, so this is, if you like, a version of the fundamental theorem of algebra, because if you want to solve for the roots, is just evaluating how many values that will make this number 0. So if you like here, if you maybe I will just put it here in this this equation here. If you just rewrite it, then you have u to the power n minus z, or z minus u to the power n is equal to 0. So it's just like finding the zeros of this equation is equivalent to finding the root. So in this case, if I have a number, and here I need to underline here complex number, of course, under the complex number. So this is important here. Now this from the first look here, it might be a little bit confusing, because what does this say? Let's go back to the previous example. So we said that according to this, 8 has 3 distinct third roots, according to this. Okay? Under the real numbers, we just saw in the previous example that 2 is a root, right? 2 is a third root of 8. But 8 is a complex number, isn't it? Is 8 a complex number? What do you think? Is 8 a complex number? Is 8 a complex number?
Yeah, it could be like 8 plus 0i.
So it is a complex number, right? Of 8, which is equal to 8 plus 0i. So it's a pure real number, but it is included in the complex numbers, okay? Now, what does that mean according to this theorem? It says this must have exactly 3 roots, right? We have 2. This is in fact the only root in the so-called real numbers, under the real numbers. So we have 2 other roots under the complex numbers. Later we will see that how to evaluate them. So there are another 2 more roots in the complex number C. Okay? Actually, if you think about it, one, we will see maybe an example how to evaluate the roots of unit. 1 to the power 5 has 5 roots. Can you imagine that? We know only 1 root, which is the real number 1, but it has 5 roots. So according to this theorem, evaluating complex numbers, let's say roots, is completely different than evaluating the real numbers roots. And here, by the way, for instance, here in the third roots, this is also a very interesting phenomena here, is that the 2 roots here that we didn't evaluate, that are still not evaluated here. In short, we'll see how to evaluate them. They are conjugate to each other. So that means here, if you have complex roots, then one is conjugate to each other. We just saw in the previous page or two pages before how to evaluate the roots of quadratic equation, and we saw that before the root we have plus minus. So if the amount under the root is negative, then I have the number and its conjugate. So always they come, if you like, in pairs. The number and its conjugate are always there. Okay. Now, how to evaluate these? Let's continue here to evaluate these. That means here we have to stop where? So 0, we have n roots. That means here we need to stop at n minus 1. Why? Because if I start counting by 0, then I have n minus 1. I have to stop at n minus 1. This is my last, if you like, counting point. Because there I am done. So I hope that it's clear for everyone that 0, 1, 2 are 3 numbers. Okay? So 0, 1, 2, up to n minus 1. These are how many values? These are n values. So whenever we are evaluating the n distinct nth roots that this theorem guarantees that they are exist, then we are going to rely on this equation here and evaluate k from 0 up to n minus 1. So these roots can be evaluated using the, let's just write the final formula of that. These n distinct roots are, so the n given z in polar coordinates n and n, then the n distinct by the way means they are not overlapping, okay? Nth roots of z are given by, let me just put here z as polar coordinates is r times cosine theta plus I sine theta. So this is the meaning. This is where I start with. This is the meaning of polar coordinates. Okay, so the roots are given by, I will call them z sub k. So here, of course, I take the nth root of r. This is no problem because r is a real number. And then my angle here, we evaluated in the previous page, is theta over n plus 2 pi k over n plus I of the same angle here. Okay, so theta over n plus 2 pi k over. Okay, so maybe here the thing is that here I have this, if you like, this is a counter running. I will, so this is k, and this is important. This k equal, it runs from 1 to up to n minus 1. So these are n values. Any question? We will solve an example in short. But before that, I want to tell you some very nice phenomena of that. Now, if I have the roots and I'm plotting the roots on the XY plane, then the roots have exactly, for instance, the fourth roots. This angle here between the roots is exactly 360 divided by n. So here, if I have the fourth root, for instance, I will be having 90 degrees. That means here, if I'm plotting the roots, they are evenly distributed. They are evenly away from each other. Okay, this is an important note. That means here, if I have fifth roots, then I will be having one root like this, one root here, maybe one root here, one root here. And each of them will be 360 over 5, which is 72 degrees from each other. Okay, so that means the roots are always evenly distributed away from each other. If I have third roots, I will be having something like 100 degrees. So I will having something like maybe the Mercedes star here, 120, 120, 120. Okay. So if you are asked to plot the roots, you will not have something like this. Two roots are very close and this one far, this one far. No, it will be evenly distributed, just like a star or flower or whatever. Okay, this is an important note. Any questions before we go to our final example here? Any question? Okay, so from my side, there are two more things we will do. First thing, we will evaluate the roots of a complex number. Maybe we'll do it very easy, third roots. And we are going also to introduce another form of writing complex numbers, which is the Euler's form or the exponential form, which is just one step, one definition. Okay, let's take the same example we used before actually. Okay, it's just evaluating or substituting in the formula. That's it. After you find the polar coordinates, find three distinct. Sometimes is the question straightforward. Third roots of the number z, let's say equal. Let's take the same number we used before. Okay, so as you see here, the question can be direct, or it can be given also as an equation. Okay, as an equation, z equals whatever to the power 1/3. Yeah, can be given that this number evaluates z to the power 1/3, which is the same. Okay, now what is n here? So let me just remind you about the formula. Z sub k equals to the nth root of r times cosine of theta over n plus 2 pi k over n plus sine of the same amount here, theta over n plus 2 pi k over n. Okay, so this is the formula. Now here in this example, n equals 3. We evaluated r, if you remember, in the previous step as square root of 2, and we evaluated theta as 45 degrees or pi over 4. Okay, let's take pi over 4 here. Maybe it's easier. So maybe here pi over 4. And here n equals 3. That means here, what is k? K equals, I need to evaluate k0, k1, k2. These are the three roots I need to evaluate. So just plugging this in the formula. So notice here that this k, once I will be evaluating this k here, I'm just plugging in here one time. First time I plug in k equals 0, second time k equals 1, third time k equals 2. If I need the fifth roots, I will plug in 0, 1, 2, 3, 4, and so on. I hope that the procedure is clear here for everyone. Okay, now square root of 2 to the power 3, we evaluated it in the previous. No, we didn't evaluate it. What is square root of 2 to the power 3? Anyway, so we will write it. I will not evaluate everything here, but just show you how to apply this formula. So the roots are evaluated as follows. The first one is z sub 0 equals 2. Now here we have the square root of 2 to the power n, which is 3, right? This is constant for all roots. Now here then we'll be multiplying, evaluating cosine of pi over 4 pi over 4 over 3. So pi over 4 over 3 pi over 12 plus I sine of pi over 12. Okay, this pi over 12 is just, if I just evaluate here, if plug in theta equals pi over 4 over 3. So if you just simplify it, it's pi over 12.
Sorry, one question, sir.
Yes, please go ahead.
You said like the nth root of r. If n is here now 3, then we would have the third root of r, and the third root is 2, is like r, and then you have the 1/3 after the brackets, not 3, right? You know what I mean?
Yeah, you have
you said power to 3, but it's power to 1/3, isn't it?
Okay, yeah, this 3 is here. So yeah, thank you. This is the 3 is here, or 6 it's here actually, right? So you're right, the 6th root now. I have the 6th root of 2, okay? Or if you like, I have the square root of 2 or to the power 1/3. It's the same, okay? So this is the square root of 2 all to the power 1 over 3, which is the 6th root of 2. Yeah, I don't know whether you're familiar to this notation, but thank you, you're right. Or we can just use this one, whatever. Okay, so this 6 here is the 6th root of 2, which is constant. Okay, clear? I don't know which notation you like to use, this one or that one. So ultimately you will evaluate it using the calculator. Okay, now the thing is, next step here, I'm going to plug in k equals 1, and then I will be ending up of having, okay, pi over 4 plus 2k. So I have here pi, so 6th root of 2 is constant. So I have here cosine of pi over 12 plus, I have here theta plus 2 pi, where's the formula? 2 pi over n. So 2 pi over 3. So as you see here, you will be just learning how to add different roots. Here, if you just have pi over 12 plus 2 pi over 3. So if you have take common factor, let's say 12, then you have 8 plus 1. You have 9 over 12, right? So here you can just evaluate it using the common denominator here, and the same here. If you evaluate this cosine of pi over 12 plus, now here I have 4 pi over 3 plus the same. So Now notice that here at the end, you will be having cosine and sine of an angle. So that means here you can evaluate this number, and then you will be getting, you can put this straight in the so-called standard form. So whenever you are asked to plot these roots, you need to evaluate it further. So here you will be getting I don't know what for instance here, pi over 12 plus 2 pi. So you have here 8 over 12, right? 8 times 4. So 9 over 12. And then you evaluate cosine, multiply this out, you evaluate this 6th root of 2, and so on. So ultimately, if you want to plot it, you need to evaluate it in the so-called standard form, because then you will be having this as an ordered pair. So next worksheet, we will solve a little bit more, maybe extensive example. But before I end, I just want to show you how exponential form, which is also called Euler's form of complex number. So exponential form of a complex number is if you are given z in polar form, it's just writing. It's just a method of writing this. Now the theory behind that is the famous equation by Euler. But for now, you need to know if you have a number z in polar form, that means z equals sum r times cosine theta plus I sine theta. Then the exponential form of z using Euler's formula is equal e to the power I theta, and here is r. Yeah. So that means here, if you want to evaluate a complex number in the so-called exponential form, you need the same parameter that you have it here. So here, all you need to do is just rewrite it. And here, very important, note